This video is going to help you determine and classify numbers as rational numbers versus irrational numbers. In 8th grade math, that's one of the biggest concepts that you start learning about first off in the school year, is being able to determine the differences between a rational number and an irrational number. In the last video, we talked about a rational number being a number that can be written as a ratio of two integers. Okay, a rational number, like I said, can be written as a ratio of two integers. Which means it can be written as a fraction. Okay? It's a number that can be written as a fraction. Now, before we go on and talking about the definition of a rational number, let's talk about what that means in terms of being able to write a number as a ratio of two integers. So, taking an example of a terminating decimal that we said was a rational number, 0.4. Okay, this is a terminating decimal. It stops. Okay, it has an end to it. Okay, so if it terminates, it's supposed to be rational. So let's show that it is rational, meaning it can be written as a ratio of two numbers. Well, if I read this decimal out loud, I have 4/10. Okay, I have the 4 in the tenths place. Whenever we want to write a fraction, as you've learned in 7th grade, you take the last digit of your decimal expansion, you find that place value, you set your decimal portion as your numerator, and whatever that place value is as your denominator. So, for example, the 4 is my digit, it's in the tenths place, so I have 4/10. Okay? Always make sure you simplify, just because your math teachers are nerds and like to see pretty answers. So when we simplify this, we get 2/5. So as you see, 2/5 is the same exact thing as 4/10. So 4/10 was able to be written as a ratio. Here's that ratio of two digits that we're talking about. That ratio, that's the ratio of two integers. Okay? 2 being an integer, 5 being an integer. Let's do another example, okay? Let's say I have, let's say we have 0.27. Okay. Again, this is a terminating decimal, and I want to show that it's rational, meaning a ratio of two digits, a ratio of two integers. Okay. So again, I'm looking at the last digit of my decimal expansion, which is 7. Okay, the 7 is in the hundredths place, so I take whatever my decimal expansion is, and I want to write it over that decimal value place value. So the 7 is in the hundredths place, so my denominator is 100. Okay, check to see if this simplifies. It does not. 27 is prime, so that's your answer. Again, you have a ratio. This is a ratio of two integers, and 27 over 100 is the same thing as 0.27 or 27 hundredths. Okay? So that's why a decimal value that terminates is considered a rational number. It can be written as a fraction. Okay? So what about this repeating? You've not learned about how to do that just yet. What we just did with writing terminating decimals as a fraction is not a new concept to you. This next concept that we're going to talk about with converting repeating decimals to a fraction, why that is a rational number. Okay, again, looking at the definition of a rational number, it can be written as a ratio of two integers. So I'm going to take a repeating decimal, let's say 0.2 repeating. Let's start with that, 0.2 repeating, which is the same thing as 0.2222, so on forever and ever. Okay? And what I want to do is I want to see, why is it that this decimal never stops, but I can still write it as a fraction? Well, there's a little bit of math magic that you can work here. Okay, and it requires you doing a little bit of algebra and a little bit of computation. So bear with me. I want to know what the fraction form, the rational form, the ratio form of 0.2 repeating is. So, and I don't know what it is, and anytime we don't know what something is in math, we use an x. So we say, I don't know what the fraction is, so let's say it's x. I do know that it's equal to 0.2222 ... Okay? Again, this represents the fraction form of the decimal expansion 0.22222 ... forever and ever. Okay. The whole goal is to figure out a way that we can eliminate the repeating decimal portion of our decimal expansion. Okay. Well, I really don't know how to do that, so let's just start doing some stuff. And I see that if I multiply this entire line, x equals 0.222 ... and multiply that entire equation, because it is an equation with an equal sign, if I multiply it by 10, I'm able to move my decimal one place to the right to give me 2.2222 ... All I did was get one repetition of that 2 out from behind the decimal. Now if I take that x that we started with and bring it back down here, and I line these up, I look at them, I'm like, oh wait, I see something. If I subtract these two lines, if I say 10x equals 2.2222 ... minus x equals 0.2222 ... then my decimal expansion eliminates. 2 minus 2 is 0. 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 It will forever do that. And then all I have to do is simply subtract 10x minus 1x, which gives me 9x, and that's going to equal 2. Okay, continuing on. If I divide both sides by 9, I get that x is equal to 2/9. Again, I was able to write 0.2222 ... I was able to write that as a ratio of two integers. So therefore, a repeating decimal can be written as a ratio of two integers. That's what makes it rational. Okay. Let's look at another example. Let's say I've got 2.141414, ... which is the same thing as 2.14 with the 1 and the 4 repeating. Again, we write the bar over the 1 and the 4 to represent that it is repeating. Again, I still don't know what the rational form or the ratio form of 2.14 repeating is, so I use x because it's unknown. But I do know that it's going to equal 2.141414 ... Now looking at this example versus the previous example, in the last example we multiplied by 10 to get one repetition out from behind the decimal. Here I've got to do something a little bit different because I've got more than one digit repeating. I'm going to have to multiply by 100 this time to get one repetition out from behind the decimal. By multiplying by 100, you're able to move your decimal 2 places to the right, and that is what gets one repetition out from behind the decimal. Again, I want one repetition to come out from behind the decimal when doing this. If I bring my original x line down, and I look at that subtraction again, I compare these two lines, I say, oh wait, because I was able to get one full repetition out, now my repeating decimal portion eliminates. It subtracts away. And I'm left with 99x equals 212. Solving this equation, 99 dividing 99 on both sides, and then I'm going to use my handy dandy calculator, unlike you, just for time's sake, in order to simplify this fraction, if it does simplify, in which it does not. So the rational form, the ratio form of 2.14 repeating is 212/99. And that is the same thing as as 2.14 repeating. I was able to take 2.14 repeating and write it as a ratio of two integers. Therefore, it is a rational number. Okay. Now, what happens if you only have one or two digits repeating, but not everything in your decimals repeating? Let's look at a couple examples of that. Let's say I have, an easier example to start with. Let's say I've got 1.12222, which is the same thing as 1.1 with just the 2 repeating. According to our definition of a rational number, if our decimal expansion terminates or repeats, in this case it is repeating, not everything's repeating, but it is repeating, it eventually repeats, okay, then it should be a rational number. Well, let's represent that. Let's go ahead and say, again, I don't know what the rational form, the ratio form of 1.12 repeating is, so I'm going to use x, and I'm going to say, okay, well that's originally what we started with, so 1.1222 dot dot dot. Now the problem with this example is that I've got a non-repeating part in my decimal expansion. So whenever I go through the process of subtracting, I'm going to have that in the way. So what I want to do is I could do one or two things, okay? I could look and say, all right, I need to multiply by something in order to get the non-repeating part out of the way first, okay? That's the first thing that you need to do, always. Okay, I've got to get that non-repeating portion out of the way. So if I multiply by 10, if I multiply that line by 10, I'm able to move that decimal one place to the right, and now I'm left with a normal problem that I'm used to. Okay. Now if I'm looking at just the decimal portion of this number, I see that only twos exist here. Only the repeating part exists here. If I bring my x down at this point, let's see, I just want to show you, do not believe that this is the way to do it. Okay. If I bring my x down, I end up getting, a portion of my 2's go away, but I still have a number in my decimal. And I can't have that. I can't have that because, and the real reason I can't have that is because when I simplify and I continue going, all right, I can't have a decimal within my fraction. That's a compound fraction, and I don't want that. So what I need to do is I need to come back. I need to say, okay, well that didn't work. So let's think here. I was able to get 10x. Okay, I did get that non-repeating portion out from behind my decimal. Okay, but I never got one full repetition out like we have previously. So we need to get one repetition out from behind the decimal. If I multiply these equations by 10, I'm able to move that decimal place one more time to get one repetition out. 10 times 10 gives me 100x, and that's going to equal 112.222. If I bring my original red line down, okay, if I say, all right, I'm going to subtract 10x from here, all right, now I notice that when I do this subtraction, my repeating portion of my decimal expansion eliminates and subtracts away. So now I can continue on about my business. 100 minus 10 gives me 90, and that's going to equal 101. Okay. Divide both sides by 90, and I get that x is equal to 101 over 90, which is the same thing as 1.12 with just the 2 repeating. I was able to write this as a ratio of two integers, so therefore it's a rational number. Okay. One more example, kind of give you the hardest one that you could ever see, that you'll probably ever see. Let's say I have something like 2.1245 with the 4 and the 5 repeating. Now again, this is the most difficult one that you'll see. Again, I don't know what the rational form, the ratio form of this number is. I know that the number is rational because it does terminate or repeat. In this case, it repeats. So I'm going to write this unknown ratio as x, and I'm going to set it equal to what we start with. So 2.12454545. Now, as we did in the problem to the left here that you see on the screen, the first thing that we did was we multiplied by a number to get one full, or well, really to get the non-repeating parts of my decimal out of the way. Well, if I look at this, I have 2 digits repeating, so ultimately I want to move my decimal 2 places. In order to move the decimal 2 places, that means I've got to multiply by 100. If I multiply by 100, I'm able to get the non-repeating portion of my decimal out from behind the decimal, and now I just have the repeating portion behind my decimal, which is what I want. Okay, now coming back and looking at the left side also, the next thing I did was I multiplied that new line that I just wrote by another number by a power of 10 in order to get one full repetition out from behind my decimal. Well, if I want to get one full repetition, which is one set of the 45s out from behind the decimal, I've got to multiply by 100 again. So I'm going to multiply both sides by 100. Unfortunately, this gives us a pretty large number. I get 10,000 x, which is going to equal 21245454545 ... forever and ever. I bring my red line down, and I'm like, all right, now I can do that subtraction, because when I line everything up, I notice that my repeating portion can subtract away, can eliminate. And now I'll just do my normal subtraction. So I get 9. Okay, I know I'm talking to myself, really kind of crazy. It's okay. So now I'm just kind of going through this process of solving that little equation in order to find what the decimal expansion of 2.1245 repeating is as a rational ratio number. Okay, so 21033, 21,033 over 9,900. Okay, let me just double check on my handy dandy calculator to see if this number will simplify, because I like simplified answers, and my calculator is saying, I don't understand. So I'm just going to leave it as this. And again, 21,033 over 9,900 is the same exact thing as 2.1245 repeating. Okay, these are the same thing. I was able to write that as a ratio of 2 integers. Therefore, it is a rational number. Okay, now what I want to do is I just want to kind of briefly and quickly go through some examples of classifying and determining I want you to classify whether the numbers are rational or irrational. Okay. Now this is a big problem that you'll probably see on your state test, because this is one of the big concepts of 8th grade. It's being able to determine rational numbers and comparing them to irrational numbers, and being able to determine whether they're rational or irrational. So let's look at an example here. Let's say we've got 0.14256. Okay. This first example, just looking at this example, I say, all right, well, that decimal expansion is really ugly. It doesn't look like it's repeating, but the problem is that it stops. 100% it stops. Okay, because that decimal stops, we say that this number is a rational number. It doesn't matter how ugly that decimal is. If that number stops, it can be written as a ratio of 2 numbers. Okay. In this case, I would look at the last digit. I'd say, all right, what place value is that? I got the tenths, the hundreds, the thousands, the 10,000s, the 100,000s. So this as a ratio would be 1,4,2,5,6 over 100,000. Now, I know that simplifies, but I'm not going to go through the process of doing so. This is a rational number. That's what is the idea that I want you to see. All right, looking at pi. Again, hopefully you know by now that the number pi is approximately, and it's not equal to, because you cannot say that pi is equal to anything. Pi is approximately 3.14159, and so on, so on. There's no pattern. It does not stop, and I know it does not stop because of these three dots. So because it does not repeat and it does not terminate, we say that this number is irrational. That this number is irrational. Pi is irrational. Okay, let's look at another example. Let's say we've got 4, something kind of easy. Well, 4, think about it. Can you write 4 as a ratio of two integers? Well, yeah, you can. 4 as a ratio of two integers is the same thing as 4 over 1. 4 over 1. 4 divided by 1 gives me 4, so 4 can be written as a ratio of 4 to 1. So therefore, it is a rational number. Okay, another example. Let's say I've got the square root of 16. Well, the square root of 16 is equal to the square root of, well, is equal to 4, because 4 times 4 gives you 16. And since 4, as we just determined up here, is a rational number, this number, the square root of 16, is rational. Okay, another example. Let's say we've got the square root of 20. Well, the square root of 20, what does that equal? What number times itself gives you 20? Well, there isn't one. There isn't a number that gives you 20. And in fact, if I type this in my calculator, I get that the decimal expansion is approximately 4.4721359, blah, 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 blah. Therefore, you can tell that this number does not have a repeating portion in the decimal or does not terminate. It goes on and on forever. Your calculator might tell you that it stops, but it really and truly doesn't. That makes it irrational. And last one here. All right, looking at another example, I have, let's say, 2.14151617, ... Well, this is a little confusing because there's a pattern to it. And just because there's a pattern, it doesn't necessarily mean that it is a rational number. Okay? The definition of a rational number says nothing about a pattern. It says, does your decimal expansion terminate? In this case, it does not. It does not because I see that ... Or does it repeat? Well, look at the decimal portion of this number. What is repeating? Nothing's repeating. And since nothing is repeating, this number is irrational. This number is irrational. Alrighty. Like I said, this is one of the big concepts that you first start learning about in 8th grade math, and it's very important that you're able to classify and determine the difference between a rational number and an irrational number. Just kind of in closing, a rational number is a number that can be written as a ratio of two integers, which means it can be written as a fraction. And as we saw in this video, you're able to write terminating decimals as a fraction, and you're also able to write repeating decimals as a fraction. Okay? So because you can write those numbers as a ratio of two numbers, two integers, it is rational. Numbers that do not or cannot be written as a fraction or a ratio of two integers is an irrational number. Some examples of that are a pi. You've got the square root of non-perfect squares. Those are going to be irrational. And any other number where the decimal expansion is not repeating or not terminating. There might be a pattern, but that does not make it a rational number. Something has to repeat or it has to stop in order for it to be rational. If you have any questions, I hope that you will comment below. Otherwise, I'm going to draw my little silly face over here. Whoops, he's got a weird eye. And I hope you guys have a great day.